So in this hexagon, we have sine, cosine, and tangent, and the reciprocals are straight across. So this one is going to be cosecant, and everything we're going to do today is supposed to have a theta on it, but we're just going to leave the thetas off because we're not actually looking at any angles. So just to save yourself some time, leave the thetas off. This would be cotangent, and this would be secant. That's C. Now, the identities we need today are the reciprocal identities, Pythagorean, product, and then we're going to prove the product ones. Okay? So the reciprocal identities can be seen straight across. So the first one would be sine equals, and notice there's a 1 in the middle, so sine is 1 divided by cosecant. 1 over cosecant. Yeah. Okay? So the other one would be secant, another one would be secant equals 1 over the cosine. Or also cosine equals 1 over the secant. Okay, now I'll let you finish those on your own time. So look at the Pythagorean identities. The Pythagorean identities are going to be the ones that we use the most today. Isn't that going away? Okay, there we go. The Pythagorean identities are found by looking at the black triangles. So notice there are 3 black triangles. They all have the same orientation, and the Pythagorean identities are found by starting on the top left and going around clockwise. So the first one is sine squared, so this one, plus cosine squared is equal to 1. So write that down on Pythagorean identity. Sine squared plus cosine squared equals 1. Why do you suppose it's called a Pythagorean identity? Is it? The Pythagorean theorem is a squared plus b squared equals c squared. Is that what we have? Kind of. If we look at the unit circle, and we draw a triangle in the unit circle, the length of the ground is known as cosine. So this is cosine, and this is the sine, and the hypotenuse is 1. So a squared plus b squared does equal c squared. So this is the Pythagorean theorem in the unit circle. And if you take the sine of any angle and square it, and the cosine of any angle and square it, those two lengths will add up to be 1 every time. Yes, has to be the same angle. There are instances where one angle and another angle would work, but it has to be the same theta. That's right. Okay, another Pythagorean identity would be here, tangent squared, so we start here and we go around clockwise, plus 1 equals the secant squared. And if we wanted to, we could actually manipulate this using our change it into sines and cosines trick, and it would turn into that. But we're not going to. Okay? But all of these identities can be manipulated to create the other identities. What would the last one be? What would this Pythagorean identity be? 1 squared plus cotangent squared equals cosecant squared. And that's just another version of the Pythagorean theorem. Okay? But there are 6 more spaces. Because that's, the ones are in different places because you follow this way. It doesn't really matter. You can switch them back and forth. You'll see them both ways. But that just happened to be the order they were shown. Okay, so can this be written another way? So normally we'd rewrite the Pythagorean theorem a squared plus b squared equals c squared. Could we write it in terms of a squared? What is the Pythagorean theorem in terms of a squared? c squared minus b squared. So I can write this in terms of sine. Sine squared equals 1 minus the cosine squared. Is there another way to represent it? Cosine squared equals 1 minus the sine squared. And that's going to come in handy. Your original reference sheet only has 3 Pythagorean identities. The one we're creating now has 9, which will be 3 times more useful than the other one. So I'll let you finish the Pythagorean identities on your own. Now let's go to the product identities. And secant. So I'll help you in a minute, Abe. Pay attention to this. For the product identities, any trig value on this hexagon is equal to the product of the 2 adjacent vertices. So you pick any one randomly. Tangent. The first product identity is tangent is equal to the sine times the secant. So write that down, and then you'll notice the last question says, prove it. No, it's easy. How do you prove that sine times secant is tangent? So we could turn this into 1 over cosine. So sine times 1 over cosine is sine over cosine, and that is tangent. So we're done. Okay. The next product identity, sine of theta is equal to the 2 adjacent vertices, tangent times cosine. So tangent of theta times the cosine of theta. How do I verify that that's true? Change the tangent to sine over cosine times cosine. Cosines cancel. Sine equals sine. So I did it right. Okay. So let's try another one. Let's do secant. So the secant is equal to the tangent times the cosecant. Well, what is the tangent in terms of sines and cosines? Sine over cosine. And what is the cosecant? Well, cosecant is 1 over sine. You don't need the reference sheet. This tells you right here. So 1 over sine. Well, the sines cancel, and I'm left with secant equals 1 over the cosine. Is that true? Yeah. If you look here, secant is 1 over the cosine. Good. Okay. Go ahead and finish that paper.